I think we might head towards the final session of this workshop, if people are ready to go again. So we have the last talk, closing in style, with a talk by Tim Harris on lattice QCD constraints on the thermal photon rate. And then after Tim's talk, we'll have a couple of words from the three of us to summarize some aspects of the workshop. So Tim, I'll hand over to you if you'd like to start.
Okay, thanks. Yeah, it's a pleasure to give the final talk of the workshop, which was very enjoyable. So today I'll talk about.
So just before you start, Tim, you're not sharing your screen yet.
Yeah. Thanks.
After all this.
Yeah, exactly.
Tests.
After all the checks. I mean, so
Very
can you
good.
see?
Perfect.
Can you
Yes.
see the screen? I can't see you. So yeah, you can see the slides on the cursor now.
We can see the slides and the cursor, and even you as well, actually. So it's all working perfectly.
So yeah, today I'll talk a bit about our work with Marco, Harvey, Aman, Ariana, and Chaba on the photon rates, which we published last year. And I was asked also to give a few words about some recent progress on multi-level integration algorithms with fermions. So I hope I'll have some time at the end to recap that recent work and maybe give some perspectives. But I'll start with talking about this work on the thermal photon rate. So in a heavy ion collision, for example, this data is from Alice, from the lead-lead collision for the yield, the differential yield of photons as a function of the photon transverse momentum. And this yield is comprised of photons from many different stages in a heavy ion collision, from the initial hard reactions, thermal production, and also hadronic decays. And the thermal component is what we're interested in, because from that you can infer some properties of the thermal medium created in the collision. And the thermal production rate is known so to leading order in the electromagnetic coupling. It's determined by the vector spectral function evaluated at light cone kinematics. So here Q is the charge factors for the three light flavors. Alpha is the electromagnetic coupling, and here's the Bose distribution. And as I said, for real production, we're interested in this spectral density evaluated at light cone kinematics, so zero virtuality. And one possibility for realizing this zero virtuality condition is that the real frequency is equal to the real momentum. And of course, we heard from Harvey as well, there are other possibilities for reaching this kinematics. But in this work, we'll talk about the fixed spatial momentum dispersion relations and trying to extract this density from the usual fixed spatial momentum dispersion relations. And of course, this week we heard, I mean, this is a differential observable, but of course, this week we've heard a lot about integrated observables. And I mean, really to produce these rates, you need to integrate this against in some hydrodynamic model to predict the thermal production. So, I mean, here we're doing the classic thing of trying to understand the more differential observable, but of course, you know, there's been a push or a focus to thinking about what observables are really interesting, which can be obtained by integrating these spectral densities against some known kernel. So the spectral density, of course, is defined as the imaginary part of the retard correlator, and here it's the correlation function of two conserved electromagnetic currents, and because and where the bracket denotes the thermal average. And of course, because the currents are conserved, we know some quite strong constraints about this spectral density, in particular that it has in the small frequency limit due to the charge conservation, it has this charge diffusion pole. And I mean, this holds non-perturbatively, so it's a prediction from hydrodynamics. the question is, we don't know at what scales exactly this hydrodynamic prediction sets in, but it must be there in the soft limit. We know quite a bit about the spectral density in QCD at next to leading order for light cone kinematics in the time-like regime, and recently also in the space-like regime. And this work was partly motivated by the study, the non-perturbative study I'll show later. And we also know the asymptotics in QCD and the deep time-like regime at very high orders, because this is basically just the vacuum spectral function. So in other theories, we also know some results. For example, in supersymmetric theory, we know both the weak and strong coupling results, and this is quite instructive. In fact, the plot on the right-hand side is the production rate as a function of the photon momentum. The dashed and dotted curves are for the weak coupling in the weak coupling regime for different values of the coupling in this theory, and the solid curve is the strong coupling result. And you can see that in the small photon momentum limit, they have extremely different qualitative behaviors, and we'd like to be able to, in QCD, to discern between these two types of scenarios. So above the chiral crossover temperature or close to it is the medium strongly or weakly coupled, or the quasi-particles or not. This is what the kind of qualitative information we'd like to discern. So I'd like to briefly just outline some work which I'll compare to later, which is a Quenched study from the Bern-Bielefeld group, of which Olaf was an author. In this case, they examined, so they computed the Euclidean vector correlator in the time momentum representation for a few different values of the spatial momentum. And in order to, and of course there we have the usual spectral representation with this given kernel. And in order to constrain the spectral density, so the trace of the vector spectral function, they used a polynomial ansatz for small frequencies and subtracted the contribution which is given by basically the vacuum spectral function at large frequencies. And the results are shown, so for the spectral density as a function of frequency for 3 different values of the momentum here with the solid blue curves. And the relevant kinematics for the thermal photon production rate are given by the black vertical bars. So in order to extract the photon production rate, you want to evaluate the spectral density for a given momentum on the light cone, and that corresponds to looking at the spectral density at these points. And you can see that there's a large, so especially at larger momentum, there's this diverging background from the vacuum spectral density gives a large contribution. So the photon rate they extracted in this, basically the light cone spectral function with a given normalization is given in the lower plot. So exactly corresponding to these three momentum. And the curves here give the NLO QCD prediction, so they're not a fit to the data for these 2 different temperatures. And you can see that as you go to the small momentum limit, it's very difficult to control the lattice QCD results. But in general, they see quite good consistency, especially for the larger momentum with the perturbative case. And the strongly coupled spectral function is basically flat with this normalization and is about this value 0.15. So this is really challenging, and this so the existence of this UV divergence makes it extremely challenging. And also, of course, so the Euclidean correlator, you can see very clearly is sensitive to so the time-like and space-like kinematics. I mean, the correlator is the integral over the spectral function, which includes non-light-like kinematics, which is not really what we're interested in here. So the first observation as part of this other work is that we can define another spectral density which is sensitive to the same light cone physics. And this observation is based on the fact that the rest frame of the thermal bath breaks Lorentz invariance, so that this the general tensor structure for the vector spectral function, the general tensor is given in terms of 2 tensor structures, transverse and longitudinal. and this means transverse and longitudinal to the spatial momentum. And if you look at the traditional choice of the vector spectral function where the Lorentz indices are traced, this corresponds to basically the sum of the transverse and longitudinal structures. However, on the light cone, there's a word, well, I mean, we can apply the vector word identity, and this actually tells you that on the light cone, the longitudinal structure vanishes identically, but it vanishes just for the light cone kinematics and is non-zero elsewhere. But it does mean that on the light cone, the spectral density is independent of this longitudinal structure, so you can add or subtract as much of this longitudinal component as you like, and this will change the behavior of the spectral density of the light cone. So this is illustrated in the following slide. For example, instead of looking at the sum of the transverse and longitudinal, we look at the difference. And this again, this takes the same value on the light cone, but off the light cone can have very different properties. And according to Lorentz invariance, this difference vanishes actually in the vacuum. And this means that the spectral density is finite at finite temperature without any subtractions. So it means it's more sensitive to the thermal physics. And also one inversion method which hasn't been discussed this week is the method of Cuneberti. And I think one of the requirements to apply this method is that the density doesn't have such a divergence. So this is illustrated in the right-hand plot for the spectral density at leading order, that is the contribution from free quarks. So the traditional channel, the sum of the transverse and longitudinal, is shown with the dashed blue curve, and you can see that this diverges in the ultraviolet. And the light cone rate at the leading order, so the light cone rate would be given by evaluating the spectral function at the dashed line, vanishes at leading order. But if you look at the difference, the T minus L channel, you see that, again, the light cone rate is not altered, but instead of having this large diverging background, it's actually very small and negative above the light cone. And in fact, however, the below the light cone, the density is enhanced. So here we have the phenomenon that the density on either side of the light cone has changed, but the light cone rate is not. So this offers an alternative to extract the light cone rate. So you can also apply the operator product expansion to this channel, and you see that it has a very soft behavior in the ultraviolet. And in fact, the T minus L channel satisfies this sum rule, which shows you that it must change sign. And at leading order, it indeed changes sign exactly around the light cone. So we investigated this T minus L channel non-perturbatively by computing the Euclidean correlator in coordinate space as usual, with two flavors of order A improved Wilson fermions. And we took particular care to try and obtain a reliable continuum limit. So we have lattice spacings down to 0.03 Fermi. We used 4 independent discretizations of the correlation function to study the systematics of the continuum limit. And we also investigated quite a number of different momentum on and off axis. And these lattice sizes go to 96 cubes, so they're really state-of-the-art lattice sizes. And on the right-hand plot, I show you the correlator in coordinate space as a function of the separation between the two currents. And you see the 4 different lattice sizes, and the continuum limit is marked with the black points. And you'll note that the correlator varies quite slowly. And this is because, in a sense, we don't have this UV subtraction. So the y-axis here is a linear scale. So it's really quite a slowly varying correlation function, and it means, which corresponds to the fact that it doesn't have this large UV divergence. So this is an example for one of the momenta. I don't think I'll have time to go through to this. So I'm going to skip just to how we constrained the rate. So how we dealt with the inverse problem, which I think is worth going through a bit more detail in this, given the audience here. So we introduced a model, a Pade ansatz for the spectral density with basically 2 independent poles. And the reason that we chose this model is because it accommodates the fact that we know that there must be a pole, this diffusion pole, basically which sits along the imaginary real axis, and for small enough frequencies has to be there, predicted by hydro. And it also satisfies the UV asymptotics, and it accommodates a sharp change of the spectral density around the light cone. So the PATE is quite a flexible ansatz. And furthermore, we impose some physics constraints on this model, that the rate must be positive. We explicitly ensure that the sum rule is enforced, and we also impose this this other interesting physics constraint, which is that basically none of these poles should get too close to the real axis, and that corresponds to the fact that we don't believe in the chirally symmetric phase. There should be long-lived resonances, or any rates, rates which should get too large. So basically, we take the fact that these poles, or there should be no rate which gets larger than the minimum of the weakest of these two possible long correlation lengths in the system. One being the charge diffusion, the rate of charge diffusion, and the smallest value that this can take is the one given in the strong coupling theory that we know of. Or the other rate, which can be large, is the rate of this damping of a static current, and the smallest value that this could take would be if you chose the one from a weakly coupled QCD. So we took the weakest possible constraint of the two to avoid any solutions which would be basically incompatible with our physical kind of intuition about this scenario. So in order to actually extract the spectral density, rather than doing a maximum likelihood fit, we sampled the chi-squared for this problem kind of in a brute force way, where we also did a bit of a global fit in the momentum range. So we parameterized these pole positions in the momentum. So we did a global fit for a few momentum correlators. So, or for a few momentum at once. For example, the lowest three momentum we fit together with a global ansatz, or we look at the chi-squared of that system. And in fact, we have an over-constrained system here, with the number of degrees of freedom being 12. And for the larger momentum, where we expect the photon rate to be varying more smoothly, we chose to look at the chi-squared for the global fit for larger groups of momentum. And we have even more degrees of freedom available in those cases. So looking at the chi-squared landscape for this lowest group of momentum here, we show the samples of the chi-squared distribution and against the corresponding values of this effective diffusion constant, which is basically the thermal production rate. And you see that basically the smallest chi-squareds, there's no clear minimum. Here you can see that there are chi-squareds which are very close together and give rise to quite different values of the photon rate. So in order to make a very conservative procedure, what we did was basically quote the width of this distribution from all possible samples with a p-value greater than 0.3, or basically with a reduced chi-squared less than 1. So in this case, for example, this would give us a range of the observable we're interested in, basically from these two values. So the spectral density, the resulting spectral densities, which correspond to some of those samples, are shown here for example, for the lowest momentum channel. The three colored solid lines give examples of the spectral densities which give an acceptable chi-squared, and the dashed curve is the leading order spectral density, while the dashed curve is the one from the strongly coupled theory. And you can see there's a family of solutions, and again here we would take all possible solutions here, and this would give us a value for the thermal rate at this frequency or momentum. corresponding to the difference between the largest and smallest values. So we validated this approach also for the perturbative and supersymmetric spectral densities, and it did indeed bracket the spectral densities for the. So we believe that this was a very conservative approach to obtain a final result for the photon rate above the crossover transition temperature. But still, we get non-trivial results for the spectral density normalized in this way. So this is the spectral density as a function of the photon momentum, and you see here the bands which correspond to the final ranges which were consistent with our data. And this is to be compared with the earlier Quenched study. And you see that we still don't have the resolving power with this conservative bound to discern between the strongly coupled scenario or the weak coupling prediction. But nonetheless, these are non-trivial constraints. And I don't think I have time to talk about the transverse channel, other than to say that Csaba gave a talk at Lattice, where we're also investigating this orthogonal channel in order to pursue an approach which is more similar to the one of the Bern-Bielefeld group. So in the last few minutes, I'll just want to give a recap of the work we did recently, or which is ongoing, about multi-level integration with fermions. So just a quick recap of what the strategy is with multi-level integration and why it might be relevant for, it might be relevant also for, let's say, the inverse problem. So just to remind you that for the standard Monte Carlo sample mean, the variance of such an estimator goes inversely proportional to the number of samples. And this is quite problematic because it means it's very difficult to reduce the error. If you want to reduce the error by a factor 10, it generally costs you a factor 100 in the cost. However, there's an alternative. In theories with a local action density, the action can be decomposed into a sum of terms such that the dependence of the gauge field, by decomposing basically spacetime into these two non-overlapping regions, the dependence of the gauge field in this region, for example, omega 0, is contained only in the first term, while the dependence of the gauge field in this second domain, omega 1, is only in this last term here. And this allows you to develop an algorithm where you update only the gauge field in subdomains of the lattice simultaneously. And if you have, for example, a 2-point function where one of the operator lives in one of the domains and the second operator lives in the other, you can write an improved estimator by combining all of these n-squared samples. And the variance of this improved estimator should scale approximately like 1 over n1 squared instead of 1 over n0, up to some point at which the fluctuations in the boundary term become relevant. And this, of course, has been known for a very long time and has been applied in pure Yang-Mills theory, and of course was essential, I think, in studying correlation functions of the energy momentum tensor, and also at finite temperature, and putting constraints on transport coefficients. So in theories with fermions, of course, this seems very challenging because the fermion determinant is non-local. However, a few years ago, there was a proposal put forward by Che, Giusti, and Schaefer for a representation of the fermion determinant in which the dependence on the gauge field is approximately factorized up to basically a term which, if you have a very good representation of up to a small basically correction, which depends on basically the geometry of this domain decomposition. So the idea is instead here, in contrast to the theory of bosonic theory, is to decompose the lattice into overlapping domains, where the overlap is some physical size, and then to update the gauge field just in some subdomain of these overlapping regions. And the point is that the gauge field dependence is completely factorized up to this small point, this small term here. And if the fluctuations in this term are small, then one can develop a multi-level algorithm. So the fluctuations in this remaining term basically depend on parameters like this overlapping size. And what we've done recently is to check basically in a large scale simulation with light quarks whether this, what this size can be, and whether the fluctuations in this remaining term can be controlled. And it turns out that they can. And the application that we investigated was one that's also been discussed this week, which is basically the hadronic vacuum polarization contribution to mu1G-2. And we've seen already this week how this can be represented in terms of an integral over the vector current correlator. And the integrand here, for example, is shown on the right-hand side. And the reason that this is a particularly challenging problem is that, of course, the error grows on the integrand because the kernel is growing polynomially. And basically this can be, so the growth of the kernel actually means that the variance also grows. So to put it shortly, the signal to noise problem in this observable can be kind of boiled down to the fact that most of the signal comes from distances at this quark mass of around 1 Fermi. However, most of the variance comes from much larger distances, around 3 Fermi. And if you go to the physical point, then this becomes much worse. Here you can see, in fact, the variance, if you had a very long lattice, the variance would be finite. Eventually, the exponential decay of the variance would win, over the polynomial growth of the kernel. But it grows very fast in this up to this point of 3 Fermi. So we'd like to see if we can reduce the variance basically at long distances, and then eventually the exponential decay of the variance will win over the sorry, I know I'm a little bit over time, but I think 2 slides left. Is that okay?
Yes, of course.
Okay. So this is exactly, so what we measured was in this 2-level simulation with light quarks, we measured the variance of this integral, this integrand. So in the standard setup, so with standard Monte Carlo, you can see that this, note the logarithmic scale here, the variance does indeed grow very sharply up until around 3 Fermi. But with the multi-level Monte Carlo integration, we chose here n1 equals 10. You can see that this growth of the variance is in fact basically killed by the multi-level algorithm. And at large distances, you get a reduction in the variance of a factor 100, even though a priori you've put in just basically a factor 10 times in the 10 times the cost. So at this point, the main study was to verify that the variance does indeed behave as you wish. This is not a priori, known. So, this is still work ongoing. The observable itself is not factorized, and comparing directly with the different algorithm isn't completely simple. But the ultimate goal, the fact that the variance does scale at long distance, like 1 over n1 squared, is also not a priori known. So this was the goal of that study. And okay, in the last slide, minus third minute. What is this? So we know that multi-level integration has been essential in the past to make some challenges more tractable in the pure gauge theory. So what about opportunities for tackling challenges, you know, in QCD, also at finite temperature, where, I mean, the fact that you have to introduce this this slightly larger scale in the factorization of the problem maybe would raise some questions about the applicability at finite temperature. Well, we saw yesterday from Harvey's presentation about this new idea for or this new set of dispersion relations which relate the Euclidean correlator at a fixed virtuality to the spectral density also at a fixed virtuality. And he showed a very nice plot of the integrand for this zero virtuality correlator, which we're working on with colleagues at Mainz. And you'll see that this integral relation looks similar to the one for G-2, except here the kernel is exponentially growing. And in the plot, what I've shown is the integral kernel for the HVP. This is actually the result we got with the multi-level integration, where you see now that the growth of the error is not so bad, up to 3 Fermi. And this is actually, and here I show the integral kernel for this this exact zero virtuality correlator, actually with the same physics parameters modulo the lattice spacing. And you see that you encounter obviously a very similar signal to noise ratio problem. And I mean, this indicates, or this, I mean, this I suppose shows the close analogy between these two observables. They're both vector current correlators, and they both share very similar challenges. And because this is a screening correlator, of course, in the spatial direction, you have as much space as you want to let's say introduce new factorizations of the lattice. And you really need to solve this signal to noise ratio problem if you want to go especially to higher Matsubarra modes, which is basically analogous to higher momentum correlators. So this certainly seems like an interesting application of those methods, and basically because of the very close connection between the two things that we've investigated. So yeah, that's okay. I should really finish up now. So what I discussed in the first part of the talk was extracting the photon production rate from the usual fixed spatial momentum dispersion relations. This is still challenging, even with introducing quite a lot of physics input. And of course, it would be interesting to understand if there are other ways to introduce this information. I mean, this is one thing that is certainly relevant to this workshop. I mean, rather than maybe introducing the type of model that we did, this is ongoing work, and we're currently investigating the transverse channel, which is a nice cross-check with the same lattice data. And in the second part of the talk, I just gave a very brief recap of the progress of multi-level integration algorithms with fermions, and and I showed the results for applying these kind of ideas to the hadronic vacuum polarization contribution to muon G-2, and maybe there's a class of problems which are very similar, and of course we would like to be in this situation where you're dominated by, a different challenge to the typical inverse challenge. I mean, if you're dominated by noise in the correlator, maybe this is another way to view the problem. So thanks for listening, for those of you who are still here. And yeah, sorry, I've gone a bit over time.
No, that's fine. That's great. Thank you, Tim, for a really interesting talk of two halves, if you like. So thanks so much for that. So we have time for some questions. Alexander, I think, yes, you have a hand up.
Hi, Tim. So in the Quenched QCD derivation of the multi-level algorithm, locality is really crucial. And if you're now introducing these subdomains, For a non-local action update, can you be sure that you're really just changing the variance, or are you also tampering somehow with the means by any chance?
So sorry if that, yeah, I mean, I really didn't have much time to explain this. So all of the non-locality is in this term, and we include this term in the simulation. It's included as a reweighting factor.
So this is taken into, yes,
it's taken into account.
Okay.
So the question that you might ask is if if all the fluctuations go into this term, I mean, that would be the problem.
Mm-hmm.
And what it seems, I mean, so what are numerical, I mean, it's very difficult to answer this a priori, but the numerical experiments suggest that with a domain decomposition like the one I've sketched here, the fluctuations are completely under control, which is kind of remarkable, right? So
interesting. I didn't get that thought before, but now it makes sense. So I mean, you correct for the non-locality, and you see that you're still winning because the fluctuations are actually somehow damped down by the part that you're treating with the multi-level approach, and then the reweighting somehow is not as affected as one would have maybe naively expected.
Yeah, I mean, this depends. Yeah, I mean, so the two things that can kill you are the fluctuate. I mean, you have to make sure that this is correct. I mean, this is really inequality, right? Mm-hmm. So this is really just a representation of the fermion determinant. And so a priori, it's correct. I mean, you have to make sure that your, you know, however you simulate this part is a correct convergent, you know, is an algorithm which correctly represents this part. So that's done with the multi-boson part. And then this is the only part left over which is non-local. And I mean, so what we do is we just measure this term, and the only thing that can mess everything up then is that all the fluctuations are somehow still in this non-local part, and then you don't win. But that's not the case. I mean, okay.
Yes. So
we understand why that is the case, but then I mean it was disingenuous to say we don't understand why that's the case. I mean, the motivation for choosing this representation is because we believe that this should be small and should have small fluctuations. And indeed, when you do the full simulation, you verify that that's the case. The second thing, which is non-trivial, is to ensure that the variance of the observable is not dominated by those same fluctuations. I mean, basically, you have to put the reweighting and the observable together to make sure that you get the variance reduction, which is dominated by. So your variance has to be dominated by the variance coming from these two independent domains. Essentially, at some stage, you will be dominated. I mean, just like in the pure gauge case, there's, you know, within this, so at level 1, there are some parts of the field which are not updated. If your observable is dominated by these modes, of course, then, you know, you could put, so, you know, you can also, if you measure the Wilson loop, which is defined on the links here in the boundary, of course, its variance will be independent of the number of sub-updates you do. That's clear. So this is also something that's non-trivial for the fermionic observable, and that's why we did the test, right? Is to check that this is not the case. Yeah. So so explicitly, I mean, also you see that this depends on the distance between the currents. So that if you were looking at a pure gauge observable, it might be much closer to being a factor 100 everywhere. But I mean, there is some non-trivial dependence here of the variance, of the variance in the multi-level setup on the distance. It's for the value n110, it just happens that the longest distance that we achieve, it's kind of a coincidence that this looks flat, but the dependence with the distance is not trivial either. So.
Thanks.
Kefe?
Yeah, it's very interesting results you have. I was just wondering what the overhead you will need to get this multi-level. For example, take n1 equal to 10. How much computer time, relative computer time, do you need to generate these configurations?
This is a good question, and it's something which is not. So it's not super obvious how to compare with the HMC, because these multi-boson fields, they're basically just pseudo fermions. Mm-hmm. So I think in the example, the number of these multi-bosons was on the order of 10. So it's not dissimilar to the number of multi-bosons that are the number of pseudo fermions that would use in the strain, if you're doing the RHMC. Mm-hmm. Now, the operator which appears in here is also not the usual d-dagger-d. So you also have to account for that. So we have every indication that there will be an overhead, but there's no reason to believe that the overhead will kill the gain. I mean, this exponential gain at all. I mean, it's basically amortized by this gain. I think there's some more comments in the paper, more concrete comments in the paper about the extra cost of including the multi-boson fields. But off the top of my head, I mean, so that's why I wrote it here. I mean, I can't give you a number and say it's, of course, it depends very strongly on the physics parameters as well.
Yeah, but even with the power growth, it will be useful for to get the exponential gain in the signal.
Yeah, exactly. I mean, that's the hope is that, I mean, exactly. I mean, this 1/n² gain is, I mean, it will basically amortize, I mean, this kind of overhead.
Thank you.
Yeah. I think you have to check the paper and see if there's I'm not sure if we give really an actual concrete cost comparison. I mean, it's extremely implementation dependent as well.
Yeah.
Okay, so
we did the simulation. That was the point. I mean, we did the simulation, and I mean, maybe an obvious question or an obvious point is that in the paper we computed all of the light and strange contributions, including the disconnected, to G-2 up to 3 Fermi, and got about 1% error, and without using any bounding. I mean, we really computed the contribution up to 3 Fermi. So, I mean, it's not. It was quite tractable given the resources that we had.
Good, thanks.
To produce this N1. So that was with N110 and N025. So it was, let's say, if the updates were cost exactly like they would in the HMC, it would be, we generated, let's say, 250 updates. And yeah, we got the statistics of 2,500, if you like, standard updates for the long distance. That's the equivalence that we had.
Okay, so thank you so much, Tim, for a really interesting talk. So just thanks once again. And with that, I think we come to the end of the invited talks and towards the end of our workshop. And so the three of us spent a little time this morning thinking about how we might put together our thoughts and offer some perspectives. And so Anthony, I think, has some slides, and we might formally close the meeting then with Anthony's slides. So I'll hand over to Anthony.
Yep.
Yep.
So I'm sharing the slides already. And going into full screen so that you can
Yes, you're there.
see.
Yeah.
Okay, so we had a great time with this workshop, and it's difficult for us to now finish up. So we start with a bit of a football quote here, which is, after the game is before the game. We have spent an entire week discussing, and this is third in this chain of workshops, but it is clear that with all the gains made, there's still a long way to go. And in these few slides, we try to kind of show the directions that we have been seeing, or the things that we found particularly interesting during the workshop. And that is, so I've just lost thought. I just got a message. One more time. Okay, attacking the inverse problem. What did we learn? What did we discuss this week? And one thing that we found really interesting was, which we then paraphrase now from Max's discussion slides, is this set of broad picture questions. So the central goal, of course, is reconstructing the spectral function encoded in the data. And how do we get there? And some things that we discussed on and off over the entire week, and I thought was shown very nice in this broad overview discussion session, is like, how do we characterize even the severity of an inverse problem, or our particular inverse problem, for all the different applications we have? What is the role and what are the sources of systematic uncertainties? There is a huge landscape actually of different reconstruction methods, and we didn't even have representatives of all methods here this week. And how do we categorize that? What is how do we classify which methods are good for what their drawbacks, what their benefits are? One thing that came up on Tuesday in particular, where we had the condensed matter day, was what is the role of regularization? Because we had the suggestion of dropping regularization completely, which was then followed up with somebody saying, well, never ever do that. So these kind of detailed questions also play a role. Are there opportunities to circumvent the inverse problem? And we've had some very impressive examples during the week showing how that can be done. One question there that is also related with newer topics is, what is the benefit of Minkowski time? We haven't talked about it explicitly in this workshop. This might be something for the future. However, this is something that is being hotly discussed also in what we saw, for example, with Stefano's talk with the quantum technologies coming up, where in principle, Minkowski time correlation functions might become available in the future. Then the cross-community dialogue and exchange. This was part of the Max at this point. Are we constantly rediscovering rediscovering each other's methods? And that really, there was also some other comments like, oh, you have exactly the same problem we have, we just give it a different name. So that really shows the broad applicability and the importance of the dialogue and exchange with these other communities. They might learn something from us and we might learn something from them. And an open question really is also the roadmap for progress, and also what the expectations are. And we hope that this workshop gives like a small nugget towards finding such a roadmap and pinning down the expectations. One part of this, of course, was the methods, the strategies to attack the inverse problem, and this was nicely discussed in the guided discussion led by Alexander, I think, which is to have these three strategies where we say we cannot solve it, so we will avoid it. We can solve it, so we will focus only on data, or we can solve it and we will add as much information as possible, what the different challenges are in this. And I think this three strategies slide that Alexander had really nicely kind of encapsulated what is going on there, and how that how we can come together. It being important that as practitioners, I thought this was interesting to see also comparisons between the different methods, but we as practitioners have to also broaden our horizon to the different strategies. We cannot just like be focused on one. We might lose out on something important for our favorite method. So some takeaways that Sinead, Alexander, and myself came up with is that Something that was already the premise of the workshop, but was really very highly confirmed, is that the inverse problem occurs in exactly the same way in many, many different fields and many, many different observables. There's really a common enemy or common problem here. And what we really enjoyed was this kindled conversation between these practitioners to explore overlapping interests. I think some mentioned throughout the workshop, oh, they had not been really aware of these ideas using smeared spectral functions, and I find them really interesting. And I think also the other way around, the people have said like, oh, this particular Bayesian method or stochastic method I never heard of before, and it's really interesting to see how this could be incorporated into my favorite method. I think we all raised, everybody knew, but we also reaffirmed the severity of the science problems we are encountering. Of course, some seem harder than others. This is part of this landscape question. I think we are still not quite clear how to answer that landscape, that severity characterization question. And I think we really transferred some nice knowledge during the week, different applications. I learned new methods. I learned new applications where you can do this. And this gives us an idea for future directions, perhaps towards the next workshop, perhaps organized by one of you in the audience. That would be amazing, of course. Which is, we could of course branch out to an even wider community. What we didn't have is these projection methods, like Pardee methods, even though Tim touched on this in his last presentation. It did not feature prominently, so we might change the order a little bit and put it more in the front. We did not have anybody really for ridge regression, so these machine learning methods in detail, which is something we might want to explore a little bit more, just to understand it a little bit more. And also that this, something that I didn't really understand, which was mentioned, is this application of denoising. How does that work in reality? How is that really related to our inverse problems, and are there other applications for us than there? We have the 3 strategies which should be further discussed. We have a landscape of methods which should be further discussed, including in particular their strengths and weaknesses. And we should continue to extend the dialogue. With this, we want to acknowledge once more the support we have received through the Strong 2020 network from the European Union. I think there was also a chat thing a second ago. That's the thing that threw me off. There's an important thing, that is, if this has sparked any publications, you need to put the acknowledgement to the StrongNet support. There is a text block that you have to do for that. However, that information will be available through the secretariat, if I paraphrase this correctly. However, yes, we acknowledge the support here. And we especially want to thank Barbara Gazzoli, the secretary of the ECT STAR, who's always been there for us to sort out the technical things and get everything set up. But most of all, we want to thank the invited speakers and all participants. Like, without you guys, it would not have been this fun. Like, discussions don't work if nobody talks, and everybody spoke and got into it and mentioned something. The talks were excellent and on point, always really focusing on the topic of the workshop. We are really grateful, and you're really the important part of the success. And we really hope that next time we can meet in person. That would be really amazing to have some coffee break together, and yeah, perhaps there can be some champagne to post and chin with everything that we have learned. And with that, I want to say, yeah, I guess we can close the workshop. I think the link will still be live. If there's any more discussions you want to have, of course you can. However, the official program is done. And also this slides will go online in the intro and outro session, so that you can also find the link, for example, to the recordings, so that you can rewatch any presentation that you missed, or that you found extra interesting and wanted to have another look at, or if you want to check yourself out if there's something you want to fix. So the link is down here. And with that, I have another look at the chat if there's any other message. And no, so thank you guys. It was really awesome.
Everyone.
Thanks everyone. Have a great weekend.
Thank you very much.
Thanks.
Thank you.
Goodbye.
Bye-bye.
Bye.
Bye, everyone.